Welcome to this short video on OLS asymptotics. This is a very brief version of chapter 5 of Wooldridge's book. Follows directly on chapter 4, which was on inference when we assume normality of the error terms. And as I said, it's a very short introduction. I'm going to briefly motivate this, then I'm going to talk about consistency, afterwards about asymptotic normality and large sample inference, and finally about asymptotic efficiency, and here we get back to the Gauss-Markov theorem. So what's the motivation for all this? So far we have focused on finite sample, small sample, exact properties of OLS. So we have not really talked about the sample becoming bigger or anything like this. And also all I've said when I discussed inference in the slides for chapter 4 was we're not really dependent on the sample size. We have talked about unbiasedness under the first 4 assumptions, MLR1 up to MLR4. We have talked about OLS being the best linear unbiased estimator under these 4 assumptions plus the assumption of homoscedasticity, and we've talked about normality when we add the assumption of normality of the error terms. And then we've basically talked about inference, making use of properties of these test statistics. It was the case, and we have not gone too much into the details why that is, but it is the case that the T statistic has a T distribution, and the F statistic, the F test, has an F distribution, hence also their names. Now, all this was based on the normality assumption, then this holds actually exactly. Now, the beauty about asymptotics is that we actually don't need to assume normality of the U's, the distribution of the U's. Instead, we can make use of a result from statistics, the central limit theorem, that says that averages are normally distributed. That's one, and the other thing that things converge under certain conditions, and convergence means that when n grows, that the distribution concentrates around the true value. Let me elaborate a bit more on this now. So first of all, what is then the case is that in large samples, properties hold approximately, even if we don't make specific distributional assumptions on the U's. And even without these assumptions, approximately these T and F statistics that we have seen have approximately in the limit T and F distributions in large samples. So that's great because what that means is that we can actually use all the things that we've seen in chapter 4 without assuming normality. As long as we can think of our situation as one in which we have enough data, which normally is actually more and more the case because we get more and more data for our empirical analyses, so at least more and more observations. And again, what's the reason? The reason is that the limit of the T distribution is the standard normal distribution, and the limit of the F distribution is a chi-square with the numerator degrees of freedom. And in some sense, we've seen some of this already when we looked at the tables for the percentiles of the distribution of the F distribution and of the T distribution. When the degrees of freedom became big, then things became approximately normal for the T and approximately actually chi-square for the F distribution. Good. So this is all very brief, but I think enough for you to get a bit the idea where all this is going. So let me now go into the details and tell you what consistency is. So many useful estimators, and this now goes beyond OLS, right? So think of all kinds of estimators, right? So many useful estimators are actually not unbiased. OLS is unbiased, and that is special, but we're going to see in chapter 15 the IV estimator, IVE, here, and that one is actually not unbiased. However, we still want them to have, say, reasonable properties, and what we have agreed on in the profession is that consistency is a minimal requirement for estimators. So Clive Granger, Nobel laureate, said, if you can't get it right if n goes to infinity, then you shouldn't be in this business. So consistency is about letting n go to infinity. So beta hat j is a consistent estimator of beta j if we can make it arbitrarily close to beta j by collecting enough data. That's the idea. And what holds, in fact, and this is summarized in theorem 5.1 in the book, is that OLS is consistent. So under assumptions MLR1 up to MLR4, beta j hat is a consistent estimator for beta j. What we need actually for consistency is a weaker version of MLR4. So MLR4 was the zero conditional mean assumption. And what we really need for a consistency is a slightly weaker version, and that is a zero mean and a zero correlation assumption. So the expectation of U should be 0, but that's innocuous, as we've argued before, and the covariance between X, J, and U should be 0 for all the J's. All right, so we don't even need this slightly stronger conditional mean assumption, but they're very close, so I don't want to spend too much time on this. How can we think about consistency? So let's say, for various sample sizes, n1 less than n2 less than n3, I get distributions for my estimator beta 1 hat, and the true value is beta 1. Okay, so what is this distribution? First of all, let's recall that in the back of our mind, we should think of getting a data set, getting our estimate of beta 1, getting a new data set of a certain sample size, with a certain sample size, getting a new estimate, beta 1, doing this many, many times. So then each time I get an estimate, and then I'm looking at the distribution of these estimates. So what I see here is that when I go from less observations to more, to even more, then the distribution is concentrating more and more and more and more around the true value. All right. And this is what we mean by consistency. So when we push this further and further and further, then we get more and more observations, and then we get closer and closer and closer to the true value, or put differently, the likelihood that I'm a certain amount away from it actually goes to 0 when n goes to infinity. That's the definition of consistency. Asymptotic normality is now about the distribution of the estimator. Under normality of the U's, what we have seen is that actually the distribution of our beta j hat given the axis will be normal, and here we generalize this. And as I said already in chapter 4, the exact inference required this normality assumption, MLR 6. If I don't make this assumption and I just use the first 5, then I can still establish asymptotic normality of OLS. What this means that in large samples, approximately our estimators are normally distributed even without normally distributed U's. And the reason is that these estimators, in the end of the day, take averages of the data, so they will also take averages of the U's. And if you take averages of the U's, then you have already normality coming into play, because there is the central limit theorem saying that an average is normally distributed. And that's simply a very big result in statistics. Let's put it like this. And since this is true, I'm approximately in the situation in which I am in chapter 4. So therefore, I can basically do all the things that I could already do in chapter 4. So I just have to use the exact results from chapter 4 and let the number of degrees of freedom, the degrees of freedom go to a large number. And for that reason, I can just use all these results. All this is summarized in theorem 5.2 in the book. That's asymptotic normality of OLS. And it states that under assumptions MLR1 up to MLR5, beta j hat is asymptotically normal with mean beta j, and that sigma square hat is a consistent estimator of sigma square. And third, what it says is that this quantity here that we have seen before when we looked at chapter 4, the estimate of beta j minus the true value beta j divided by the standard error of beta j hat, so the estimate of beta j is asymptotically standard normal, and in that sense follows a t-distribution. So you see quite some parallels to what we had before. Finally, asymptotic efficiency. There's a result that we've seen before, namely that OLS is blue. And efficiency here in the context of asymptotic analysis means that under the assumptions 1 to 5, the Gauss-Markov assumptions, the OLS estimators are the best linear unbiased estimators and also asymptotically efficient. So also best in large samples among estimators in some appropriate class. I'm very vague here, I know that, and it is a bit technical, so I will actually leave it at that, with the aim of just giving you a little bit the idea what is going on here. So the big picture point here is that we get normality, and that we can do what we already did in chapter 4 when it came to inference, even without assuming normality of the error term. And that's great because, as we have said in chapter 4, sometimes normality will really not hold. And what we really can use is that averages follow a normal distribution, and that's all we need. In that sense, things fall into place even without us making this normality assumption. The small, I would say, caveat is that this holds only for large samples, whereas the results in Chapter 4 do actually hold for small samples. So if you have 5 data points and you estimate 3 coefficients, then the distribution of the estimator will be normal, because linear combination of normally distributed random variables is normally distributed. However, in practice, nowadays we often have lots and lots of observations, so asymptotic normality is, in some sense coming for free, because we have large samples normally in our applications anyway. So in that sense, this is a very, very brief treatment of all this. I hope it still gives you a little bit the idea, and as I said, more details are reserved for some other time. With this, all the best.